session, modeling Smectic liquid crystal elastomers. James Adams from University of Surrey.
No, there should be a microphone. Yes. Do you have the microphone?
Yeah, I have it.
Yes.
Completely forget it.
Right.
Maybe take this off because otherwise.
Yes, so I'd like to thank the organisers for giving me this opportunity to speak, in particular Mark Warner. So I'd like to talk about modelling liquid crystal elastomers. So various aspects of this talk have been introduced by other speakers we've had so far, smectic liquid crystals, spontaneous deformations, and we saw how layers deform in the previous talk as well. So the outline of my talk is as follows. First of all, I'll talk about some experiments on smectic liquid crystal elastomers to give the basic mechanical properties that we're trying to explain. Then I'll talk about Gaussian models of these smectic elastomers and how we can calculate their relaxed energy, so we can minimize the energy over the various microstructures that you obtain when you stretch them, and then briefly talk about some extensions to the smectic C phase. So we've seen the smectic phase then in John Toner and Randy Kamian's talk and various other talks. So this is a layered phase, and what I'd like to talk about is what happens when you start to stretch that phase. So in the smectic liquid, when you stretch it parallel to the layer normal there, you start to see buckling of the layers, and that's because the system would like to keep the layer spacing the same, and the way it can do that is by shearing perpendicular to the plane of the layers and forming these undulations. The layer spacing is very stiff, so it has a bulk modulus typically of about 10 to the 7 pascals in the smectic phase. The details of this were looked at in X-ray scattering patterns in the 70s, and what people saw there was that in these highly perturbed structures you could get undulations not only in one direction, as I've shown here, but in two directions, so perpendicular to the plane of the boards, and you end up with structures like the inside of an egg carton. This deformation, this buckling of the layers in liquid smectics is eventually relaxed out by the propagation of dislocations into the smectic phase. So you can manufacture then, or smectic liquid crystal elastomers have been made. We've seen before there are various ways you can connect the liquid crystal mesogens onto the polymer chain. The easiest to explain for the smectic phase, in fact the one that fits the model, is the side chain type. So this is where you don't incorporate the mesogens directly to the polymer chain, but you just connect them onto the backbone. And in siloxane-based elastomers, you can make a monodomain sample by applying a mechanical field or an electric field and so on, with a rubber modulus of about 10 to the 5 pascals. And they still have this liquid smectic modulus for changing the layer spacing of about 10 to the 7 pascals. Look at these things in the X-ray scattering, then you can see small angle scattering peaks here that correspond to the layer spacing, and as you stretch the sample parallel to the layer normal, the small angle scattering peak splits into two, corresponding to the buckling of the layers. Some of the X-ray scattering intensity is lost here, so you also see some rotation of the layers perpendicular to the plane of the X-ray scattering pattern that I've shown here. We'll come back to that a bit later, so remember this small angle scattering part. So as I said, they have highly anisotropic properties. Mechanical properties depend on whether you stretch them perpendicular to the layer normal or parallel to the layer normal. If you stretch them perpendicular to the layer normal, then the sample remains transparent, and it has Poisson's ratios of 0 and 1. So in the direction parallel to the layer normal, the sample doesn't contract at all, and all the volume conservation is done by contracting in the plane of the layers. Whereas if you stretch parallel to the layer normal, then the sample becomes opaque, which is associated with this buckling transition, and you have Poisson's ratios of 1/2 in the two directions perpendicular to the stretch axis. So this sample is contracting isotropically in this direction and in the plane of the board. Their mechanical properties are highly anisotropic, so in the perpendicular direction you see the rubber modulus. In the parallel direction you see the Smectic modulus. And you see when you stretch parallel to the layer normal, you see this buckling phenomena. So when you get up to a few percent strain in this particular case, then you see, instead of the liquid Smectic modulus, you see something much more like the rubber modulus. So there are various frameworks in which people have tried to explain this. I'm going to talk about a model based on phantom chain Gaussian networks. So we assume that we have a collection of anisotropic Gaussian chains. We can do a quenched average and get something like this Neo-Hookean elasticity formula. I'm going to use F for the deformation gradient tensor. There's some difference in the mathematical and I think the physics community here, or lambda in the previous talk. So please remember the affine deformation here is given by F. There are some other techniques of doing this. So Lagrangian elasticity theory we saw in the previous talk by Tom Lubensky and others. I'm not going to talk about this model, but you can show that it's equivalent to the to this trace formula type approach. So we've seen the trace formula already for the pneumatic elastomer. And we've seen these two tensors here. L0 tells you about the initial anisotropy of the polymer chains, and L inverse tells you about the state in their, the orientation of the anisotropic chains in the deformed state. In addition, in the Smectic phase, we have another term that says how difficult it is to change the layer spacing. And it comes with a different modulus, this this Smectic layer modulus B. So there are two types of objects in the system. Then there are these polymer spans that, when you stretch the system, deform and rotate towards the stretch axis. And then there are these embedded Smectic planes. The previous speaker spoke about how the Smectic layers deform. So to work out how a Smectic layer deforms, you consider two vectors in the plane of the layer. Each one of those vectors deforms affinely with, so like these embedded vectors, so f dot the vector that you're deforming. And then if you take the cross product of those two, you find you get something like lambda inverse transpose. Another way to write that is just cofactor of the deformation matrix. So our Smectic layers, layer norm will deform like cofactor of the deformation matrix dotted with the original matrix. And if you work out what sort of thing that does when you stretch the sample, the layers try and rotate so that they're perpendicular to the direction of deformation. And as the previous speaker explained, you can calculate the layer spacing by projecting onto the new layer normal. So these are the different ingredients then in this model of Smectic elastomers. Note that the direction of the director, which is parallel to the layer normal, is now fixed. There's no freedom for it to rotate around and give rise to things like soft elasticity, so you don't get soft elasticity in Smectic A elastomers. So this model works relatively well. You can substitute into it an affine deformation with a shear, and what you find is for the first part of the deformation, when you stretch parallel to the layer normal, the layer spacing increases, and so you detect this liquid Smectic modulus, and the sample's very stiff. And then when you get above the threshold, then you start to get shearing of the layers, and instead of changing the layer spacing, you just stretch the chains, and so the modulus drops then to the shear modulus of the rubber. There's a mathematical relation between these two slopes. You can find that the ratio of the two essentially give you the position of the threshold. And somehow the cloudiness of the sample should be explained by forming these textures that Antonio mentioned earlier. Right. So there are some more experiments that support the deformation of the layers as this cofactor. So Chris Billman and co-workers have constructed an acrylate-based Smectic that's been aligned using an electric field. There are some complexities with the relaxed state of the sample, which means the smectic layers are still tilted a bit with respect to the stretch axis. But if you, what they've done is measured the X-ray scattering pattern of this material by shining an X-ray source here and then rotating the sample around this axis phi, which means you can collect X-ray data from a whole range of different directions and find out what happens to the X-ray scattering that you lost that I mentioned at the start of the talk. So there's some loss in intensity of the smectic layers. So these plots show looking down on the top of the scattering pattern that I shown earlier, so they'd be in the plane perpendicular to the board. So we're looking down on these small angle X-ray scattering patterns here, and as you stretch them, you can see that they start to spread out in a circle here. And so these are the layer normals spreading out on the surface of a sphere, and so they're stretching in various different directions, both in the plane of the scattering plane that we saw earlier and perpendicular to that. So this is strong evidence that is consistent with the layer normal deforming as the cofactor. So the layers really seem to be like embedded layers in these side chain systems, both in the siloxane and the acrylate systems. There are some systems that are much harder to explain using this kind of side chain model. So perhaps some more weakly ordered smectic systems shown here. So if there seem to be some defects in this side chain elastomer, they still show the same threshold and then softening after the threshold when you stretch parallel to the layer normal. But the sample still remains transparent when you stretch parallel to the layer normal. So perhaps there's not this microstructure, and correspondingly the X-ray scattering here doesn't show any rotation of the layer normal, at least in the plane of the X-ray scattering pattern. The main chain systems, which I haven't spoken about so far, are also much more difficult to fit into this sort of theoretical model. So when you stretch the main chain systems, the layer normal, so the small angle scattering that I've shown here, still remains in the same position, so there's no rotation of the layer normal. And the sample still, but the sample still has this shoulder when you stretch parallel to the layer normal. So there are some aspects here that are quite difficult to explain with this type of elastic model. So far I've talked about uniform deformation. Suppose we'd like to explain, we'd like to do some more realistic deformation geometries and find out what happens at the edges of the sample. So we can do arbitrary geometries. Well, we can look at the free energy that I mentioned before, and if you plot it out as a function of the deformation parallel to the layer normal in the z direction, and then a shear, you can see that it's a non-convex energy, which is, again, the signature that you're getting some sort of microstructure formation, as we saw in the pneumatic phase. So this is just a contour plot of this surface here, and you can see the fold that I've shown here appears in the level sets over there. So this is a multi-scale problem. You've got to understand what's happening at the microscopic scale. There's some buckling length scale here that's the geometric mean of the sample size and the size of the layers. So perhaps instead of doing this multi-scale modeling, we can follow a similar route to Antonio and co-workers in pneumatics. So we've seen there that you can calculate the quasi-convex energy, which has these stripes in that Uriyama doesn't see in his experiments. So the trick there is to go to the high temperature state. So this is the one way to write the high temperature state in terms of these singular values of the deformation tensor F and the spontaneous distortion, so this value A that we saw earlier. And you can calculate the quasi-convex energy, which has various microstructures associated with it. So can we do a similar thing for the smectic phase? So this is just the definition of the quasi-convex function there. We need to find some deformations that obey the kinematic compatibility requirements that Antonio talked about, and we can connect them together, and we can we can choose these deformations such that they're both in the energy wells that I mentioned earlier. So choose deformations that are in these energy wells, but average macroscopically so that they give you the deformation of the sample that you require. And then if you can make a sufficiently fine mixture of these, you can obey the boundary conditions. And then we can put this sort of energy into a macroscopic finite element calculation and work out what happens when we deform our sample. So the first thing to do is to, instead of working in the low temperature Smectic A phase, so when you have this sort of energy with these L tensors, it's more difficult to see what's going on. So transform to the high temperature deformation, the high temperature isotropic phase by using a composition that includes the spontaneous deformation, in which case you find that the free energy is given by this expression, provided that the determinant of F is 1. So you get something that looks just like a neo-Hookean term, and then this second term that tells you about layer spacing. So this is simpler than the nematic phase, and what's happened is there's some of the terms from the spontaneous deformation that have gone into this deformation, this term in the energy, which is why you get a different value of Q here. So essentially you have to complete the square. We've also made an approximation that K is very large, so this cofactor F dot N norm is approximately Q, so we can write it as in this slightly simplified harmonic way instead of having the cofactor in the denominator, which is what you'd have in this sort of expression. But as Randy said at the start of the week, hopefully these all reduce to the same sort of theory of Smectic, so we should be okay. And what's nice about this is for a simplified energy, and if you take a two-dimensional example, you can show explicitly how to make its relaxed energy just by considering rank 1 connected deformations. So this is the free energy that I wrote down on the previous slide there, and I've written out the cofactor explicitly in terms of the cross product of two vectors in the initial plane, so E1 and E2, and then deform those with F. So that's just what the cofactor is doing. Here's my coordinate system here. E1 is normal to the film. E2 and E3 are in the plane of the film. So let's think about a plane strain sort of deformation here. So nothing happens in the E1 direction, so that's in the film normal, and all of the deformation here is in the plane of the film. If you substitute this into our energy here, then up to a constant coming out from this trace part, you get the same neo-Hookean bit for the first part of the energy. Then the second part of the energy simplifies because F E1 just remains E1, and then you've got E1 cross whatever F does to E2, and you can just write that as norm G E2. And so this is the simplified two-dimensional version of our Smectic A energy. And then if you substitute in a deformation here G, but with this additional part, so substituting in some sort of shear here, so this gives you two rank 1. This will give you a set of rank 1 connected deformations with some amplitude S here. You can substitute this into your energy. There's a bit that remains unchanged because this trace G transpose G will have a bit GE3 squared and a bit like GE2 squared. The GE3 bit doesn't change when you substitute in this deformation. The GE2 bit you can combine with this second part here and just have a function psi that depends on GE2. And this is the bit that's non-convex. And it looks like this plot that I've shown here. So this is for both negative and positive values of this GE2. And you can see it's got a minimum here. So you'd like to choose the value of S in your deformation, the extra bit of shear that you've got, to change the value of GE2, which will change the value of psi to be in the minimum of your energy. So that will just give you whatever the shear happens to be. And you're essentially solving this formula here for T. So it's some sort of parabola, and you get two solutions, and they're your two deformations that you can substitute back into the energy. And what that does is flatten out this bit of the energy because you can always sit in this minimum with the right amount of shear as you deform the sample and change this GE2 down here. So that's where you get your convex energy back from and iron out this fold that I showed you in the energy earlier. As Antonio said yesterday, it's a bit more complicated in 3 dimensions, but nonetheless the same thing can be done. The trick there is to write the energy in terms of 2 convex parts. So the first bit is lambda max, so the maximum singular value of this matrix here, so the deformation matrix dot this projection matrix. So this tells you how much the maximum value of the deformation perpendicular to the initial direction of anisotropy. So if so it's this maximum value in the perpendicular plane, and then d is another convex function. So it's cofactor f dot n naught, so the layer normal, and this part tells you how much you've deformed the sample parallel to the layer normal, more or less. So if you stretch parallel to the layer normal, then this term d will decrease like 1 over the amount that you've stretched it by. So the quasi-convex energy then has a few different regions that I've shown in this plot over here. This is the equilibrium point in terms of these new variables b and d. This top corner here I've called anisotropic solid. There are no microstructures in this particular region, and you can just stretch the sample and use the previous energy formula I described. Then there are 2 other regions, the green region here, which I'm going to call the unidirectional buckling region. This region has first-order laminates, so just some mixture of 2 gradients that I explained, or Antonio explained yesterday. Here's a depiction of some buckled layers, so this is just a mixture of 2 shear deformations. So that's the unidirectional buckled phase. And then you can show that you need a second-order laminate in this red region. So they're the layers within layers that Antonio mentioned. But there's a problem in this region of the quasi-convex energy in that it's completely flat. So the sample doesn't care so if you stretch the sample parallel to the layer normal, it doesn't care what the deformation is perpendicular to the sample. So you should be able to squeeze it then in the perpendicular direction and just increase the size of the sample in the perpendicular direction somehow. This isn't observed in experiment. If this were true, then the Poisson's ratios wouldn't be a half when you stretched parallel to the layer normal. So we need some sort of additional term here to fix up this model if we're to use this quasi-convex model. And one thing to try is the second invariant of this Cauchy-Green strain tensor, which you can write something like this. So this is the Mooney-Rivlin term, and it will compress the sample it penalizes deformations in the perpendicular direction. So these 2 deformations should be equal. So what's its origin, you might ask? So it's been included in the past to account for things like non-Gaussian chains, but in this case it could also be justified in terms of deforming these buckled layers, and you can get a rough estimate for the size of the modulus for this term by using the interfacial energy and the length scale for the buckling. So you get a modulus from the dimensions of these 2 things that looks something like this. And you need this additional term to reproduce the Poisson's ratios that you see in Nishikawa's experiments when you stretch parallel to the layer normal. So let me give you a rough idea of how things work in this B and D representation. If you stretch perpendicular to the layers, so we saw in the experiments the sample remains perfectly clear in that case. So that corresponds to this F perpendicular on the diagram. So as you stretch, you just go along the B axis and you keep D the same, so the layer spacing doesn't change. And you just move in this direction, and the sample has a modulus that's similar to the rubber modulus. And if you change the value of this Mooney-Rivlin term, so this CMR denotes the the modulus associated with the Mooney-Rivlin term, then you can change the stiffness in that direction by a small amount. If you stretch parallel to the layer normal, but have a half Poisson's ratios, then you'll come down this line here at D equals B and cross from the anisotropic solid phase into this bidirectionally buckled phase. And once you cross into this phase, then you have a threshold in the deformation, and it suddenly becomes a lot softer. So that's moving down this line here. If you keep the perpendicular dimensions of the sample fixed, so you have Poisson's ratios of 0 and 1, but you stretch parallel to the layer normal, then you can move down this line here. But perhaps for experiment, it would be useful to work out what's going on in this region, in which case you'd like to first stretch parallel to the layer normal and then stretch perpendicular so that you can come along here whilst keeping that parallel stretch the same. In which case your stress-strain response here as you move along this line from this bidirectionally buckled region to the unidirectional buckled region depends on the amount of the Mooney-Rivlin term that I mentioned before. If you have none of this term, then it's perfectly soft when you stretch in the perpendicular direction. But as you increase the amplitude of this term, then you can get some stiffness in this red region there. That gives you an experimental test to find out the magnitude of this extra term that I mentioned. We can put the energy that I've been describing to this quasi-convex energy plus the additional Mooney-Rivlin type term into a finite element code now. So it's quasi-convex, it won't have these microstructures, so we can find out what happens when we stretch in various different geometries. So for aspect ratios that are similar to Nishikawa's, then when you impose a stretch here, this is shown at about a stretch of 1.4, then you get the bidirectionally buckled phase in the bulk, and then near the clamp some of this unidirectional buckled phase. But now we can do some more difficult deformations that you can't see analytically. So if you stretch at a small angle to the director, then what happens, instead of getting the bidirectionally buckled phase throughout the sample, you start to get some of this unidirectional buckled phase at the edges. And for larger angles of stretch with respect to the director, you start to get more and more of this unidirectional buckling phase intruding from the edges. And so if you eventually go to 90 degrees, then you'll see none of this phase. And mechanically, you see the threshold that we had before start to get diluted as you stretch at an angle to the director. You can also look at very long aspect ratio samples, and in which case the sensitivity to the angle of the director with respect to the stretch axis starts to get much stronger. So here, if we just change the angle that you're stretching by a degree or two, then you start to go into much different parts of this phase diagram that I mentioned before. So you should, in principle, see different microstructures in experiments until when you're at sort of 10 degrees or so, then you shouldn't see any of these microstructures at all. So for long, thin samples, it's extremely sensitive. The microstructure is extremely sensitive to the angle of the director. So there are some questions from this sort of model then. It would be nice to see some experiments of this two-step stretching to work out the magnitude of the Mooney-Rivlin term that I put in this model, if indeed it fits with the experiments. Some polarizing microscopy observations of the microstructure. So we saw yesterday that the microstructure is in fact very difficult to observe. So perhaps in Smectics it will be easier or more difficult, I don't know. We can look at the microstructure for various off-axis deformations and the sensitivity of the microstructure to the aspect ratio of the sample. Theoretically, it's still difficult to understand what's happening in the main chain systems where the layer normal doesn't appear to be deforming like an embedded layer, and there's no. So another question: what is the real microscopic origin of this extra Mooney-Rivlin term? Okay, so I'd like to say a little bit about the Smectic C phase then, and how we can extend the model that I mentioned to the Smectic C phase. So the Smectic C phase has, instead of the layer normal parallel to the director, there's a fixed angle between them. So the director can, in principle, rotate around on a cone with this fixed angle. And we can incorporate this into the model now. So we'd still have the same sort of terms, so a trace formula, but we'd have a separate director here and a layer normal, and we must take into account the layer spacing. The layer spacing can contract as the angle between the director and the layer normal change, and there's some anchoring penalty for the director to deviate from the layer normal. So these systems are much harder to make monodomains from experimentally. If you try and stretch them parallel to the layer normal during cross-linking, then, if you try and stretch them parallel to the director during cross-linking, then what you find is as they go into the Smectic phase, you end up with what's called a pseudo-monodomain. So you have an aligned pneumatic director, but the layer normals will all sit in some sort of random orientation around on this cone with the fixed angle theta with respect to the director. So this is a monodomain in the director, but not in the direction of the Smectic layers. But there are some two-stage cross-linking processes that have been done to help realize a monodomain. So if you first cross-link them under a load to get something like the pseudo-monodomain, and then you put them into some sort of shear apparatus that's shown here, and you shear the sample and then allow the cross-linking process to continue, then you can get what appears to be a monodomain siloxane-based elastomer out of these systems. And they show a spontaneous deformation when you change the temperature. So that's shown here. Hopefully you can see that. Here's the outline of a Smectic A phase. So this is the higher temperature phase of the system. And as you cool it down, then you get a spontaneous shear. Here the magnitude of the shear is about 0.4. So you can see there should be some sort of soft elasticity in the Smectic phase. But as far as I know, there are no mechanical experiments on monodomain Smectic elastomers, Smectic C elastomers. Theoretically, the energy is more difficult to deal with, but it's possible to calculate the quasi-convex hull. So this is the set of deformations that should have zero energy cost, which suggests an experiment that you might do to test this set of deformations. So if you start out with your Smectic elastomer that I've shown here, here's the director and the layer normal. If you cut out various pieces of this elastomer at different angles to the layer normal and then stretch them, you should find that for a particular angle they start to have a soft deformation, and the amplitude of this soft deformation depends on the angle phi with respect to the layer normal. The constraint of the director by the layer normal has some rather odd effects on the soft modes, though. So we saw on Friday this negative Poisson's ratios material that Tom mentioned. So Rod Lakes has thought a lot about re-entrant structures that I've shown here. So when you stretch these, they expand in the perpendicular direction, and indeed their volume expands. So perhaps there's a molecular mechanism for this sort of thing that you might find in Smectics. Professor Griffin, I think at Georgia Tech, has thought about a molecular mechanism for these sorts of things. Perhaps if you make a liquid crystal polymer with the mesogens attached in different ways, so they're either attached along the chain or perpendicular to the chain. When you stretch it, then you'd cause some of these mesogens to pop out, and perhaps you'd get a negative Poisson's ratio. As far as I know, this mechanism hasn't been shown to work very well. But the Smectic soft modes do offer one opportunity for a negative Poisson's ratio type material. I should say, though, that these are volume-conserving materials, so unlike the re-entrant structures, their volume remains the same. So although when you stretch them parallel to the, when you stretch them in a particular orientation, so as I've shown here, what happens is the director would like to rotate so it's along the stretch axis, but in fact it can't in this configuration. It first has to rotate, it has to stay on this, this orbit perpendicular at a fixed angle to the layer normal, so it starts by rotating perpendicular to the direction of stretch, which I've shown here in a plan view onto the layers here. So the director is rotating out into the perpendicular direction, which causes some lateral expansion of the sample. So it has a negative Poisson's ratio in this direction, but a much larger positive Poisson's ratio in the perpendicular direction, so it's still volume conserving. Okay, so let me summarize then what I've discussed. So I've described a model of Smectic elastomers based on some microscopic principles. We've calculated the quasi-convex free energy, which enables some calculation of macroscopic deformations of these Smectic elastomers. And we've implemented it in a finite element code, so we can compute what happens in realistic geometries, what happens for different aspect ratios, different angles of the director, and so on. So this seems encouraging, but there's a lot of experimental questions that haven't really been answered here. In the Smectic C phase, you can extend this model, and it's consistent with the spontaneous shear deformations, but there are no mechanical experiments on the Smectic C monodomains. And there's still lots of questions for the theory, such as how do you model the main chain systems? Is it possible to compute this relaxed quasi-convex energy of the Smectic C energy? So because of the constraint of the fixed angle between the director and the layer normal, this is a lot more difficult to calculate this relaxed energy. Okay, I'd like to thank my PhD student, Andrew Brown, Mark Warner, Antonio Di Simone, and various other co-workers, and thank you for your attention.
Thank you very much. Even perfect timing. You left time for questions. 1, 2, 3.
I have one comment and one question. So regarding the nature of a Mooney-Rivlin terms, right? So if you stay inside the single molecular models, of course, it's a question. How do you get it, right? But if you go beyond the single molecular model, there's no reason to assume the chains are Gaussian, actually.
Yeah.
So basically, this is not a question anymore. So then I have a question about this main chain, Smectic elastomer, right? You still see this abrupt change of slope.
Yes.
But you don't know what's happening because there's no orientation of a Smectic layers.
Yeah, right, the layers, the small angle X-ray scattering shows that the layers aren't moving, at least in the plane of the...
But have you checked the possibility that these rods start to jump to different layers?
Right, so one thing that people have proposed in the literature, at least, is you get some sort of hairpin defects, and you can start to pull these out between, so perhaps that would give you rods jumping between layers.
Yes.
Yeah, that's a good point, but I don't know of a model that includes that sort of thing.
Oh, I see. It's difficult to do theory with it.
Yeah, exactly.
Yeah, in your Smectic A model, when you were adding this cofactor term, the Mooney-Rivlin term, I'm not sure I completely followed what you were doing. Did you? I mean, you still have to calculate a quasi-convex envelope, right? I mean, can you do that analytically, or?
When you add in the Mooney-Rivlin term?
Yeah.
So the Mooney-Rivlin term is a convex term. So I guess I assume that you can add these two together and not ruin the... Perhaps I can ask you about that later.
I have two questions. So in everything that you do, you build in kinematic compatibility pretty strongly. So
Yeah.
even in the quasi-convex. So these Smectic A's and C's don't generate dislocations?
The dislocations aren't included in this sort of model, yes. In some of the Smectic experiments on Smectics, it's thought that perhaps this is what causes some of the mechanical properties rather than the rotation of the layer normal. Maybe there's something to do with dislocations. But it's not included in this sort of model, that's right.
Yeah, and the Mooney-Rivlin term that you added, without it, would your numerical calculations go as smoothly?
They would, but they would. I mean, you could still do the calculations, but they wouldn't be consistent with the experiments in that the Poisson's ratio that you get when you stretch parallel to the layer normal wouldn't be a half. they could be whatever they liked because there's no penalty for changing the Poisson's ratio there.
The zero modulus on the quasi-convex energy, that's not going to get in the way of calculations?
So, I mean, perhaps you'd need some sort of small perturbation to regularize it, yes. But there's no way for the numerics to choose the Poisson's ratio. So I think it would be set by something like the size of the clamps or something like that in the numerical simulations.
Have you considered regularizing the problem to model interfacial energies? So introduce higher order gradient terms and then spinodally decompose to see what structures emerge?
No, but I'd be interested in how to do that, I guess, yeah.
So there's one last question here from Mark.
I didn't altogether understand why people were referring to Mooney-Rivlin additions to this free energy, because the addition to the underlying pneumatic trace formula was actually an energy associated with distorting layer spacings. And I wouldn't classify that as a Mooney-Rivlin, which you have as in
Right.
an isotropic rubber.
But you need, so in addition to that, you need another term. So you have the layer spacing term in the non-convex energy. So here's the layer spacing term in the non-convex energy. If you then calculate the quasi-convexified energy, which I haven't put on this slide, it's fairly straightforward, but it's not very illuminating, I think. It has these different regions, but the BB region here is flat. So what I've done is added in this extra Mooney-Rivlin term.
Oh, I see. Yeah.
In order to fix up the Poisson's ratios.
Right, right. Thanks.
I said very last, but I saw. Okay. You asked the last question.
I did understand. I understood that the point is to calculate also the quasi-convex envelope for the Smectic sea energy, no? It's one of the points of your summary. I don't know if I saw correctly, but you have the quasi-convex hull of the set of the wells of these energies, or
yes.
not? Okay.
Only the quasi-convex hull, but not the quasi-convex envelope of the Smectic sea energy. Yes, because I think it's rather hard to
it's
compute.
already a good point, no?
Yeah.
Okay.
Okay. Before we thank James again, reminder, there's a photograph that we are going to take right now, right after the talk, and let's thank James again.